Welcome back to our Introduction to Causal Inference course. In this video, which is the continuation of part 3 of lecture 1, we're going to be continue talking about the required conditions for estimating causal effects, and more specifically today we're going to be talking about the second condition, which is exchangeability. So exchangeability or comparability can be understood as the characteristic of being exchangeable, which in our context simply means that exposed and unexposed are comparable. And by comparable, I mean that we do not have any sort of systematic bias. That is, we do not have confounding, we do not have information bias, we do not have selection bias, etc. So the exposed and non-exposed groups have the same characteristics, apart of course from whether or not they are exposed. So for us to better understand what exchangeability is and why it is useful, let us consider a simplified example where we have a randomized trial assessing the effect of aspirin, which is our exposure X, on a headache, which is our outcome Y, and let us assume that this randomized trial is a perfect one. And by that, I mean that we have 100% compliance with a prescribed treatment, we have perfect randomization, which means that treatment assignment was perfectly balanced, we have no losses to follow up, so there is no room for selection bias, and we have no sample variation, so that no statistical inference is required for estimating the causal effect. In this situation, let us think about the following question. What comparison between groups we can actually do in practice? The association between the exposure and the outcome, or the causal effect of the exposure on the outcome? By association, we mean that we are comparing the average outcome in the exposed group to the average outcome in the unexposed group. For a causal effect, we would be comparing the average outcome had the entire population been exposed to the average outcome had the entire population been unexposed. So, of course, in practice, we can only test associations because these two quantities here required for estimating causal effect are counterfactual. But if we can only assess associations in practice, even in a perfect randomized trial, why can we and do we interpret results from randomized trials, and in this case, a perfect randomized trial, as causal effects? To answer this question, and this is actually at the core of why exchangeability matters, let us think about comparing baseline characteristics between exposed and unexposed individuals, which is the first table of most randomized trial studies anyway. So what we can do here is to compare average or proportions of baseline variables in each group. And remember, we are assuming perfect randomization. So randomization produced perfectly balanced groups when it comes to baseline variables. So here, just two examples, the proportion of female sex. If it is 53% in the exposed group, it has to be 53% in the non-exposed group due to perfect randomization. So the overall proportion in the sample, of course, has to be 53%. The same rationale for monthly income. So if the monthly income is an average of $1,000 in the exposed group, then it has to be the same in the non-exposed group and therefore the same in the overall sample. So let us try to expand this reasoning a little bit further. So what about unmeasured variables? Let's say that we are interested in thinking about hypertension, but let's say we did not measure hypertension in our sample. So let us just say a generic number, say 8%, just a placeholder here for the unknown prevalence of hypertension in our sample. What can we say about the prevalence of hypertension in each study arm? That is, what will be the prevalence of hypertension in the exposed group and in the non-exposed group? It will be, of course, 8% in both, following the same logic we discussed before with regards to sex and monthly income, because the two groups are perfectly comparable with regards to any variable, regardless of whether they were measured or unmeasured. What about if we had the rather weird situation, but please bear with me because this is just to explain a concept, where we only measured some variables in one of the groups but not in the other. So here, for example, we have a situation where we have measured the variable obesity only in the exposed subgroup and the variable height only in the non-exposed subgroup. So what will be the proportion of obese individuals in the non-exposed and in the overall sample, and what would be the average height in the exposed and in the overall sample based on this information. Again, we know that exposed and unexposed are perfectly balanced. So if we have 30% prevalence of obesity in the exposed, it has to be 30% in the non-exposed, and therefore 30% in the overall sample. And the same for height. Due to perfect randomization, we have perfect balance between the groups, so you have the same average height in both of them, and therefore the same average height in the overall sample. So the conclusion that we can arrive after this thought experiment is that the exposed group is representative of the overall sample, which should make sense because when we assign the exposure using randomization, we are essentially sampling from the overall sample, and therefore the exposed subgroup is a representative subset of the overall sample. We can also see that the non-exposed group is representative of the overall sample as well for the same reason. And if they are both representative of the overall sample, they are of course representative of one another. And we could have arrived at this last conclusion simply by thinking about the result of perfect randomization, which would produce two groups that are perfectly comparable. Okay, so now that we have our table of baseline characteristics, we're going to add to our table the outcome data, which is headache, represented here by y. And this is no longer a baseline characteristic, so it is allowed to vary between exposed and unexposed individuals. So let's say here that among the exposed individuals, the ones who took aspirin, we observed 10%, and in the unexposed individuals, we observed 30%. But we need the potential outcomes under no exposure and under exposure for us to be able to estimate causal effects. So can we apply the rationale we just discussed of extrapolating results we observed in one of the groups to the other to try to fill in these question marks here? To do that, we have to remember that the observed outcome does provide information for one of the two potential outcomes. So let us think about this question. Was the potential outcome under no exposure measured in one of the groups? If so, in which one? Well, in a way, it was measured in the unexposed group because the observed outcome in this group equals this particular potential outcome. Similarly, if we ask, was the potential outcome under exposure measured in one of the groups, we could say that it was measured in the exposed group because the observed outcome equals the potential outcome under exposure in this particular group. So let us use the rationale we just discussed to try to fill in some of the question marks in the table. So we can fill in the potential outcome under no exposure for the non-exposed subgroup because for this subgroup, this is the observed outcome. And we can apply the same logic to fill in the potential outcome under exposure by copying the value we observed in the exposed group. So that's better. We managed to fill in two question marks, but what about the rest? Now we can just use the same reasoning that we applied before by noticing that potential outcome are pre-randomization variables. So we just apply the same reasoning as before. We extrapolate values that we observed in one of the groups to the remaining groups. So here we observed the potential outcome under no exposure in the non-exposed group, but due to randomization, I know that had the exposed individuals been unexposed, they would have had 30% outcome occurrence as well. And we can apply the same logic for the potential outcome under exposure. We observe 10% in the exposed group. And because we know that they are fully comparable, we know that we would have observed 10% in the unexposed group had the unexposed been exposed. And because we have 30% in both the exposed and unexposed, in the overall sample we observe 30% here, and the same for the potential outcome under exposure. But note that now we have all the information we need to calculate the average causal effect, because we have the expected value of the outcome had the entire sample been unexposed, and the expected value of the outcome had the entire sample been exposed. So we can just plug them in the formula for the average causal effect, and you're going to get minus 20 percentage points. Note, however, what would have happened had we calculated the association instead. So for the association, we would compare the expected value of the outcome in the exposed group, which is 10%, and the expected value in the unexposed group, which is 30%, and we would also get minus 20 percentage points. So this equality here is not a coincidence. It actually follows from the logic that we use to construct the table. So our conclusion here is that in the presence of perfect randomization, that is, if we have a perfect randomized trial, association equals causation. And this is because we can safely assume, notice that the word assume is underlined here, that the observed outcome in one group equals the counterfactual outcome in the other group. That's exactly the reasoning we used to infer the potential outcomes in both groups by extrapolating what we observed in one group to the other. And that extrapolation is based on the assumption that the two groups are fully comparable, which is of course the case when we have perfect randomization. And that's exactly what exchangeability means. Exchangeability is the situation where the exposed and unexposed groups are fully comparable, so I can use what I observed in one of the groups as an estimate of what I would have observed in the other group had the other group being subjected to the same intervention or exposure than the first subgroup. So this example that we just discussed could lead us to the question of whether or not the fundamental problem of causal inference affects randomized trials. Well, if we had a perfect trial as the one we just discussed, that would be correct, because in this case, association equals causation. But in real trials, the answer is no, and this is because real trials have limitations, such as failures in the randomization process, or sampling variability, which can introduce lack of perfect exchangeability. And of course, we can have other problems, such as selection bias due to loss to follow-up, information bias due to imperfect measurement of variables, imperfect compliance to treatment assignment, etc. So our overall conclusion is that in real trials, proper randomization substantially increases the plausibility of the exchangeability assumption, but it does not guarantee, and it cannot guarantee that exchangeability holds. This would only be the case if we had a perfect trial, which is more of a theoretical concept than a real concept. My main goal here was to explain to you that when exposed and unexposed are perfectly comparable, which would be the case in a perfect randomized trials, what I observed, say, in the exposed group is what I would have observed in the unexposed group had the unexposed being exposed. This is because that's the only difference between the two groups, whether or not they were exposed. So what I observed in one is perfectly representative of what I would have observed in the other had the other been subjected to the same conditions as the first. That's it for this video, guys. Please stay tuned for our next video when we're going to talk about the third condition for estimating causal effects, which is a well-defined causal contrast. See you then.